I'm going to ask you to do a couple of math problems during this exercise. They're not complicated, and you will not need a calculator. In fact, you must not use a calculator. Here we go. Yes. So, our seminar is called Modeling Wicked Problems. The thing I tend to think about in the Anthropocene context is climate change, and I'm starting with this, my favorite cartoon about climate change. I don't know if everyone can read all of this. This is about building a time machine to take us back 50 years when we should have put a price on carbon. But the really funny part is down here, somebody saying, "We better hurry." And the other guy saying, "No, that's the great thing about this technology." So this seminar is with Miriam Diamond from the University of Toronto and Pablo Jensen of the École normale, supérieure de Lyon. They can't be here tonight, but they will be here tomorrow, and we'll take off then. What's a wicked problem? Well, the name should give you a clue, but there are many, there's a classic article about this from 40 years ago. Complicated problems without a simple answer. And these people were sociologists. They were talking about the kinds of problems you might imagine, problems that are hard to figure out even how to describe them, problems in which what counts as a solution depends on how the problem is framed, and how the problem is framed determines what counts as a solution. So there's a complex process of just figuring out what you're talking about. Problems in which competing interests are involved and every interest has its own view of the problem. Things that have strong social and ideological dimensions that involve your identity, changes in basic behavior and lifestyle, what you believe. So I think you can, I'm going to try to get through this a little bit faster than my 30 minutes, so I won't go into great detail about these. I hope you can see how these apply to climate change, cannot be definitively solved, problems that we will keep trying to solve, and each element of the solution will create new problems. So one example of this kind of thing in the climate change world is the rebound effect with respect to energy consumption. So we build new renewable resources that make energy cheaper. When energy is cheap, we use more of it. If it's truly and fully renewable, that might not sound like a problem, but a lot of what happens right now is that we have hybrid systems where we're getting some of our electricity from solar power, but we're still also getting some of it from fossil fuels. The solar power brings the cost down of the electricity as a whole, and so people consume more, driving up the consumption of fossil fuel. Now, the problem that our seminar is going to look at is that scientific methods, in the classic sense, were typically developed to deal with tame problems. The whole approach of science has always been to simplify, to take things out of context and put them into a smaller and more manageable framework so that they can be studied. So here are a few classic wicked problems. Poverty. You could just give poor people money, but eventually that will run out, and where will you be then? There are many kinds of solutions to this. That part of the problem is that poverty is relative. It means one thing in one place, might mean starvation in one place, but it might merely mean malnutrition in another. Overpopulation, it's a rate problem. There's the death rate and the birth rate. You could increase the death rate, and that has been tried. It's not a very good way of solving the problem. Limiting the birth rate is another solution, and that's also been tried, for example, with one-child policies in China. If you do that, you create new problems. You do things to family structures that have really gigantic effects on a culture. Imagine that if you are in a culture with a one-child policy, After a generation or two, you have no more aunts, uncles, cousins, nephews, etc. The extended family simply disappears. And finally, tragedy of the commons type problems. Here down in the lower frame, we have thousands of people all in their cars in a traffic jam on the highway, and every single one is saying, if these idiots would just take the bus, I could be home by now. And up here, the tragedy of the commons is at the theater, I hear it lacks dialogue. There's another class of problems, of which climate change is the prime example. Super wicked problems, even more wicked. These are problems in which not only do you have all these issues about how to formulate it and what it means and how to solve it, but also you have limited time in which to solve it. The same people who are trying to solve the problem are also causing the problem, so they have a conflict of interest in the way they approach it. There is no central authority that is powerful enough to impose a solution. And people tend to think that the problem can be solved later, so they push it off into the future, and it becomes increasingly expensive and difficult to solve it as time goes on. So, like I said, I talk about climate change most of the time in these contexts, and we have this kind of problem. Let's boil this down to a human perspective. The heat wave of 2003 is a major event. This is in August of 2003, the temperature in the center of Europe rose to about 2.5 degrees centigrade on average higher than it has been historically. That doesn't sound like a lot, but it caused almost 30,000 deaths. It caused forest fires and crop damage in these areas and cost almost 10 billion euros. Why did people die in this heat wave? It's not just from 2.5 degrees centigrade higher temperatures. It was because of the character of the climatic phenomenon. Normally, in this part of Europe, temperatures rise high during the day, in the summer, but they also then cool off at night. During the 2003 heat wave, the temperature rose high and stayed high at night for about 3 weeks. That meant that buildings, for example, buildings made of stone that typically keep you cool during the day because they have a chance to cool down at night and they moderate the temperature, they eventually heated up and did not cool off at night either. Most of the people who died in that heat wave were very old, many of them old women living alone. This is a cultural issue because many of these people did not really have an understanding of how to dress for heat, and they did not have a culture of water, so that drinking water during a heat wave simply didn't occur to them, and they eventually died of dehydration. I mentioned the housing problem of stone buildings and that way of cooling things, which didn't work in this case. There was another issue, which was that the rivers that were used to cool nuclear power plants, the heat was high enough that evaporation from the rivers raised their temperatures and made them less able to cool nuclear power plants, which in France are a large part of the energy mix. That meant that they had to reduce the power output of those nuclear plants, so the electricity was not available to cool the buildings. So very complicated effects that feed back into the problem that we are facing. Now, that may seem like an isolated event, but pretty soon it's not going to be isolated, it is going to be normal or even cool. So this is the temperature of that heat wave in 2003, and the black line here is the observed temperature, average temperature in Central Europe across this period from 1900 to 2003. And then, using climate simulations to project where that will be over the next few decades, we see that by the 2040s, that temperature is approaching the normal, and by the 2080s, a summer like that will be cool. What will we do? Will we build yet more power plants to supply electricity to cool our buildings and create further climatic problems if they're based on fossil fuel? Will we build nuclear power plants, which might be impacted by that evaporation problem I mentioned, and so on? A wicked problem. So our seminar is going to do something really quite simple and basic. We're going to work with some models that let us try to understand how wicked problems can be approached. One of the things about problems like climate change is that you have both positive feedbacks and negative feedbacks that interact. And with many complicated processes going on, those interactions are hard to grasp intuitively. So what climate scientists do is build models of climate change that let them simplify the problem and try to figure out where the most important leverage points might be. Okay, here's our first math problem. This is related to the fact that we all work with models all the time because we have mental models of how things work. This is not formal, it's just a way of conceiving how you think about the world. Try to solve this problem. So you've got a piece of paper, you fold it in half, you fold it in half again, you do that 42 times in total. How thick is the paper? No calculators, please. If you already know the answer to this, fine. I'm going to give you about 30 seconds to think about this, and I would like to hear your best guess, your low estimate, and your high estimate. That is, your 95. The high estimate is and low are you're 95% confident that it's not higher or lower than that number. So ponder that for a few seconds. Okay, can I have a best guess?
It's really big.
How big? 16 millimeters. Do I have another guess?
You won't get a paper as big to hold 42 times, 40 times.
That's true, but we're doing a modeling exercise. This is abstract paper, not real paper. Yes? Sorry? 40 centimeters, another best guess. Anyone higher? Yes? To the moon. Okay. Anyone else? 4 centimeters. Okay, your highest guess, upper bound. You're pretty sure it can't be higher than this. 40 kilometers. All right. A light year. Anyone else? Okay. Answer? 440,000 kilometers. That's a far cry from 16 millimeters. What it shows is how bad we are at solving even relatively straightforward problems in our heads. And this isn't really about math. This is about your mental model of what happens when you fold paper. So the formula is very simple, and you can do this on a calculator if you don't believe the estimate. 2 to the 42nd. It's related to the classic problem about a pond where you have some lily pads, and they double in area every day, and after 30 days, the pond is full, completely covered with lily pads. On what day is the pond half full? The 29th day, right, because of course it doubles every day. So divide by 2, and that's your 29th day. All right, now let's look at a climate change problem, and I will use a very simple model for this. Bounce out of this for a second. Okay, that does not appear to be working. All right, we'll pass on that. I'll describe it instead. The carbon bathtub is simply the problem you face when you look at how much carbon we're putting out versus how much carbon natural systems can absorb. We put out somewhere on the order of 30 billion tons of carbon every year. Natural systems can absorb about 4. Where do we have to get to level off temperature increase? Most people, and by the way, on that math exercise, 95 MIT students all gave wrong answers to that math exercise as well. So the problem with the carbon bathtub is that you have to reduce the level to the same size as the input. You want to? Oh, he's unplugged the. No, he hasn't. There we go. Okay. Yep. So here we have the carbon bathtub. It's filling up. This shows the historical levels. This is carbon, not temperature. And the question is, I won't do the whole thing since I already talked about this a little bit, but if we level off carbon dioxide emissions at their current level from 2007, what happens? Well, we get a nice balance up here, but notice that the level of carbon continues to rise. So we can't just level off, we have to actually reduce by a lot in order to get to a stable temperature. Help. I can't get out of the bathtub. There it is. Okay. In modeling of all kinds of problems, feedbacks are very important. In climate change, we have both positive and negative feedbacks. It's been suggested that we should not talk about them in those terms, but call them instead reinforcing feedbacks and balancing feedbacks. The words positive and negative tend to confuse people, but anyway, the idea is that some kinds of feedbacks slow down warming, other kinds of feedbacks speed it up. Here is an example of a positive feedback. I knew I should have used my own. Yeah, you're going to have to help me. Okay. Here, I'll get through it. Yeah. F. So this is what's been happening to Arctic sea ice. This is observations, not modeling. The ice levels have been declining, and part of what happens here is that because the ice is white, it reflects radiation back into space. So it has a high reflectance or albedo that makes it cool the planet. As the ice melts, what it reveals is dark seawater, which absorbs heat and therefore increases the rate of warming. So this rate of decrease is higher than the highest estimates of the IPCC. Clouds are another example of feedback. We have two possibilities. One is that clouds, which are white, reflect heat back into space. Another possibility is that high clouds, which are made of ice, are actually transparent to that heat. So it comes in, but then they trap it on the way out. This is what a typical environmental model looks like. We have fossil fuel burning, and you see little positive and negative signs here. So fossil fuels increase greenhouse gases. That reduces the outgoing infrared radiation and reduces the net radiative forcing. Climate energy is retained. Temperature goes up, feeding back into outgoing radiation, and so on. I won't belabor this. I did want to talk a little bit about physical models in climate science. We won't be using these in our seminar, but this is what you read about when you read about climate simulation. They're huge, very complicated supercomputer simulations of what goes on in the atmosphere and the oceans. They basically take all the forces that act in the atmosphere, they transfer them from one box in these grids to another on a time step of every 10 minutes or so, and then run the model for many simulated years in order to get a climate, a simulated climate. So the statistics of that model behavior are what the outputs look like. Over time, climate models have included many more processes. In the 70s, it was really simple, just radiation from the sun, rain, carbon dioxide. At this point now, they include many other things: aerosols, atmospheric chemistry, circulating oceans, vegetation, and so on. The kinds of things we'll work with in our seminar are integrated assessment models. These are less complicated than the physical climate simulations, but they include social processes as well. Things like the economy, agriculture, energy systems, the water flows through that people use, and so on. I want to talk a little bit about the IPCC emissions scenarios because we're going to use this framework as a base for a lot of what we do in our seminar. So, a couple of times, the Intergovernmental Panel on Climate Change, IPCC, has produced these estimates of these scenarios for what's likely to happen to carbon emissions over the next century or so. Now, how do they do this? How do you get to a point where you have some clue about what might happen? The process itself is interesting. You might think that they start with modeling, but actually they don't. They start with a story, a narrative about what kind of future worlds we might imagine. So in these narratives, there were sort of two main families, the A and the B family. The A family is high economic growth, rapid technological change, and high levels of globalization. The B family is similar but moves quickly toward renewable energy supplies, and the B2 storyline is much more regional than the A1 stories, which tend to be more globalized. Then they took the stories that they generated and began to try to model them, to put them into mathematical simulations and see what would happen. So this is a very simplified representation of some of the scenarios, and what it shows is quantities, population continuing to rise and then beginning to drop later in the century, population rising more slowly here. Economic growth very rapid in the A models and less rapid in the B models. And then various other quantities, including technological change and environmental degradation. So combining those things brings them back to these scenarios, which mostly lead to pretty high surface warming by 2100. And this is actually the 2000 scenarios, which have been revised upward since then. So in our seminar, I hope I can get back out of this time.
Here we will show you how
we'll be using this model. I'm going to let him talk.
For comparing scenarios. So first let's select in the business as usual scenario, and we'll also select a one-child policy by 2030. and we will run the dashboard population to do a comparison. And here you can see the colored-coded scenarios coming up in the graph windows. And in the total population window, we can see that the total population compared to the business as usual has dropped considerably, going down to approximately the same levels in 2100 as occurred in the 1960s, 70s range. Minimize that, and to do some further comparisons, we will look at the population change rate by expanding it. And here you can see that the birth rate has gone considerably down, as you can see in the new scenario. However, the death rate has gone considerably up, and that, of course, is because the death rate has on the denominator a population which is dramatically declining. So we can close this window.
So this is called the Global Systems Simulator. It's not a perfect model. It's a model. And the reason we're using it in our seminars, it's very easy to see into this model. It has many variables. Each variable holds other variables, and those variables hold yet further variables. But it's quite easy to drill down into them and see what the relationships are that are being described. So we're going to work in the opposite direction from the SRES, the emissions scenario modelers of IPCC. We are going to start with an exercise in which people try to make the model reach a sustainable world. And it will be hard to do that. So as people work with the model, they will also be able to look down into its variables and try to understand why it's resisting what they're trying to do to it. You know, it would be lovely if we could just push down population, energy consumption, and everything else without interfering with anything. But of course, you change one, and lots of other things change too. And that's the beauty of modeling, is that it lets you look at those processes in detail. Nope. I thought it was, is it F5? Oh, I have to close the window, yeah. I did F5 and F6.
F5 and F6?
Yeah.
Oh, you did this one.
Yeah, there we go. All right, okay, thank you. All right, almost finished here. So, modeling is a tool. It's not an end in itself, and it doesn't produce answers. It produces heuristics. It helps us think about what we might need to do to reach a world that's more sustainable than the one we have. There are lots of problems with modeling. There are limits to what we can possibly know about many kinds of processes, a lot of limits to how well we can quantify them. It's really hard to take a model and then turn that directly into a policy solution that is also acceptable to large numbers of people. There may be things that are just not there in models, and we won't know that until we run into a problem later. But what they do let us do is build some degree of confidence in how we might move toward a more sustainable world in the face of enormous uncertainties. Miriam, my colleague who's going to be in the seminar, said, you can't just stop there. You have to give people some reason to hope. And I tend to be an enormously pessimistic person, but I will give you one thing that just happened 2 days ago. The US and China cut a real deal on climate change. It is bigger than it looks on the surface. It will have actually important effects on climate change if they're able to keep the policy in place. And let's hope. Thank you.